Welcome, everybody. Welcome back to those who have been here before. It is a pleasure to thank the De La Pietra families, of whom we have, for the time being, a representative, Barbara, for their friendship and the support of the activities of the Simon Center, apart from the support they provide to the university. Thanks to their generosity, we can invite stars like Edward to come here to visit us, to spend a week, and we can really learn from them, and sometimes they can even learn from us. Anyway, today we have a star in mathematics, but also a star, in a sense, in the world of media. I mean, he grew up, I think, in Moscow, and he came very young to Harvard as faculty. Then, in 1997, he moved to Berkeley, and he's been there as a very successful mathematician, but also as someone who's written books. And one of his books, which is called Love and Math, has been translated to 19 languages. It's been, there's a film that was made out of it. He also has a YouTube channel and a podcast channel to discuss mathematics. So in a sense, it's a great fact that he's someone able to communicate mathematics to the general public and inspire young people. Now, we're all very happy that he's in Berkeley, because if he were in UCLA or in Los Angeles, we could not afford him. He would probably already working with Hollywood and doing all these Hollywood films. So fortunately, we can have him here thanks to the De La Pietra families. And today he's going to give a public lecture. For those interested, there will also be a technical talk about his work on the Lang-Langs program in Thursday. And there is also a high school undergraduate lecture that will be provided on Wednesday. Okay, without further ado, please, thank you very much.
Well, hello, good afternoon, and can you guys hear me well? Yes? Okay, well, and hello also to our online audience, which I hope is non-empty. Thank you for this generous introduction, and thank you for the invitation to come here to this beautiful place, the Simon Center for Geometry and Physics, which helps me in many ways, reuniting with my old friends here and kind of feeling the vibe of this place, which is, very positive, I feel. It's a great time and place to talk about the kind of things that I want to share with you today. So, where do I begin? I want to begin with maybe a somewhat unusual place. One of my favorite books. How many of you know about this book?
Heard of it, I've never read it.
But how many of you have read it? Okay, well, that's a sizable portion of the audience. If you haven't read it, I highly recommend it. I think it speaks to a lot of things that we go through today in this turbulent, volatile, hard to predict world that's changing so rapidly. That's the beauty of art. The great masters anticipate our, troubles and tribulations, but also our moments of inspiration. And sometimes we can learn from them much more than from reading social media or newspapers and so on. At the heart, this is a love story, but isn't everything? But sometimes it's love and math also, So it's a novel by Mikhail Bulgakov, which he finished, actually he left unfinished, but he died in 1940, and it was fairly finished, his life, the love of his life, kind of stitched things together. It was banned in the Soviet Union until late 60s. And the first version that was published, about 10 or 12% of it was removed by censors. It was only much later that it was finally published in Russian. And I believe there are several translations in English, and I've heard some good things about one of them. What I want to dwell on, what I want to focus on is this maxim, what Volant, who is Volant? Volant basically the devil. It's incarnation, one of the representations of the devil, and he comes to Moscow and creates some trouble. But Master wrote a book, and in a moment of despair, he burns it. But then when he encounters Volant, Wolin says to him, don't you know manuscripts don't burn? Interestingly enough, Bulgakov himself burned the first version of his book. So of course, master represents him in many ways. And then he had to start anew and write a new version. Another famous Russian author, Nikolai Gogol, burned the second volume of his famous book, The Dead Souls, and it never came back. You know, Russians like drama, you know, so Russian artists especially. But you already knew that. So anyway, what an interesting way to talk about art. They don't burn. And of course, we can feel the truth of the statement because maybe the manuscript itself burns, but the ideas, what is behind, what is wrapped in words has longevity. However, what I want to point out is that there is one subject of human endeavor which comes close to literally exemplifying this maxim. And that subject is mathematics. Pythagoras' theorem, which we all studied at school, about right triangles, the famous equation, a squared plus b squared equals c squared. Pythagoras lived about 2,500 years ago. Pythagoreans discovered it around the same time in many other cultures, maybe even earlier. Others discovered it. Kids at school these days discover it, you know, every year. And the most amazing thing is that if Pythagoras had not lived, or if his manuscript was burned, we would still have Pythagoras' theorem. So what is it about mathematical objects and ideas that makes them so timeless, so necessary and objective, observer independent? We don't get to decide whether a squared plus b squared is c squared or c cubed, nor do we expect that this equation, this formula about the relation between these sides of the right triangle will ever change. Kurt Gödel, one of the greatest, if not the greatest logician of all time, is on record saying mathematical ideas form an objective reality of their own, which we cannot create or change, but only perceive and describe. And so the question is, what does it mean? How is it possible? And I think that it's important to address it today, especially because in today's world, we feel like there's so much conflict going on, and there are so many things that separate us. And I think it is essential to talk about mathematics as our common ground, just to see that we do have something in common. And that could be understanding that the roots of that commonality could be a launchpad for us to better understand who we are, to better understand ourselves, to better understand the world around us, our society, our relations with each other. So it is not, the way I approach it is not as something that is purely academic, is a purely intellectual, which it is a very interesting question, purely intellectually, philosophically. What does it mean? But I think it has a significance far beyond thought itself. Because I do believe that if more of us become aware of what I'm going to talk about today, it may help us to navigate this world we live in today. So, for starters, I want to contrast mathematics and physics. And this is something which is rarely discussed these days. I think oftentimes people kind of conflate the two subjects. And I think we kind of led astray. We are led astray if we do not understand the differences between them, and then also understand how they overlap and how they go hand in hand. So physical theories get updated in time. For example, Isaac Newton came up with his laws of motion and his theory of gravity. And those theories were very good to describe the range of phenomena which people could observe at the time with the available instruments of observation and so on. But at the turn of the 20th century, it was realized that these theories were inadequate for describing a range of phenomena which we could observe. And so his theory was updated. We got Einstein's special and relative special and general relativity theories, and we got quantum mechanics. Now, this did not discard Newton's theory. There is still a wide range of phenomena which are described fairly well, adequately by his work. But in some other range of phenomena, small distances, high energies, when the force of gravity is very high, the theory breaks down, and that's where these newly created theories come to the rescue. But that's not the end of the story. As I'm sure all of you know, we are here at the center of geometry and physics. Quantum mechanics is in contradiction with Einstein's special relativity. So the two theories have to be appended. Now we have quantum field theory, which in principle is more accurate, but its mathematical underpinnings are not yet clear, so we're still working on it. General relativity describes gravity and is in contradiction at the moment, one could say, with quantum field theory, and so on. So it's a quest, it's an exploration, and I don't see it as a bug, I see it as a feature. As Richard Feynman said, nature's imagination is so much greater than man's. She will never let us relax. Okay, so that's physics. But mathematical theories are quite different. They are objective, necessary, and timeless. And here, there's an important point I have to make. It's not like Pythagoras' theorem is a theorem about right triangles. Right triangles on the plane. What do I mean by a plane? Imagine this blackboard extended to infinity in all directions. And imagine that it is infinitely thin, has no thickness. And it is totally flat. It's not bent anywhere. That's a hint already where I'm going with this. There are no such objects in the physical world. There are approximations of such objects, but not the actual objects. In mathematics, we study such planes, which are infinite in all directions, which are flat, which are perfect idealized objects. They are flat, they have zero thickness. Pythagoras' theorem is a theorem about, I have to use joke too, otherwise you will not believe that I'm a mathematician. So, again, it's approximately flat, not exactly flat. It's a triangle on the plane with an angle 90 degrees. Right? So it's about this equation, a squared plus b squared equals c squared. Now, there are other geometries possible. This is called Euclidean geometry. It happens on the plane. We can also look at a sphere. We can also look at what's called the hyperbolic plane, if we are interested in two-dimensional geometries. In those other geometries, this theorem will not be true. We'll still have a notion of a right triangle, but the relation between the sides will not be satisfied. So when I say that mathematical theories are timeless and immutable, I don't mean that we stick with Euclidean geometry. I'm just saying that there is a sort of a multiverse of mathematical theories. What we call today, they're codified by what we call today formal systems, where we start with certain axioms and derive various theorems. And Euclidean geometry is one of them. Non-Euclidean geometries, or for example, non-Euclidean geometry on a hyperbolic plane is another example. Each statement may be valid in one theory, not valid in another theory. My point is not to say that somehow one theory subsumes all others. My point is simply to say that saying that it's valid or not valid is not going to change in time. If Pythagoras' theorem is proved in Euclidean geometry, it's going to stay as a theorem in Euclidean geometry. And then we could also say it has always been a theorem in Euclidean geometry. We just didn't discover it until this or that point in time. See how different, the different quality. We don't update mathematical theories in this sense, no matter what new evidence or what new technological advances emerge. So the question then becomes, what does mathematics describe? Physics obviously describes physical universe, this space, this world we live in. What does mathematics describe? And so, to get some insights into this, let's talk in more detail about Euclidean geometry. So, as I say, its objects are points, lines, triangles, and so on. And as I have already mentioned, in the physical world, we can only find approximations of these objects. if I want, I'd like to draw a straight line. When I teach linear algebra, for example, in Berkeley, I tell my students about lines and vectors and so on. So I draw this picture and I say, be careful. That's not what we call a line in mathematics. Because, first of all, it has thickness. No, and I can take a thinner chalk. But there isn't a chalk thin enough to make it, to have zero thickness, right? Nor will there ever be, it seems. Secondly, it's a little bit wiggly. If you zoom in, you'll see that it wiggles. The world is wiggly. The physical world is wiggly. But in Euclidean geometry, it is very essential that it's completely straight. Why? Because, for instance, one of the axioms is that if you have two lines which are not parallel to each other, they will intersect at one point. If you have wiggly, they will intersect at more points. It's very essential. The whole thing breaks down if you allow wiggliness in the mathematical description of Euclidean geometry. Likewise, a point of intersection, it has thickness when I draw it, but it's postulated to be totally have zero thickness. Okay, so that's, oh, one more. If you look at this, it has finite length. But in Euclidean geometry, lines are infinite in both directions, and that's essential because guess what? One of the axioms is about parallel lines. There is a unique, if you have a line and I have a point next to it, there will be a unique line that never intersects it. But how can you decide whether it ever intersects it if you can't kind of grasp these lines in their entirety? But there are no such lines. We cannot observe such lines in the physical universe for the simple reason that the universe is, what, 13.7 billion years old, give or take, and the speed of light is finite. So we only observe, the observed universe includes only things of finite length, you see? Now, so you see, this is all to say that mathematical objects are not found in the physical world. We do not perceive them through our five senses. So where do they come from? And more interestingly, why is it that nobody raised a hand and said, I don't know what you're talking about. I don't know what you mean by an infinite line. Everybody understands it. We all have, it seems, the innate capacity to conjure them up, to imagine them without any effort, even though we never seen them. Now, somebody could say, yeah, but we've seen similar things, like the ones I have just drawn. But similar things is not enough. There is a certain sense of certainty that our understanding of it, that your understanding of it is the same as mine. You know, I've been teaching mathematics for 30 years, so I can speak to that. Nobody has ever said, I don't understand what you're talking about. Now, some people may not have had a chance to learn it. So in other words, that muscle is kind of underdeveloped. That's fine. Well, there's some people for whom some of the five senses are not as developed as for others. That's fine. I'm not saying that everybody has equal understanding at the moment. But in principle, I believe everybody can develop it, right? So that's very interesting. But let this example not fool you. In this example, there are still objects in the physical world which are similar to the abstract idealized mathematical forms. But for the vast majority of mathematical objects, there is actually nothing at the moment that we can see in the physical world around us. For one thing, right now I observe a three-dimensional auditorium, three-dimensional space. Three-dimensional meaning that there are three, I can draw three lines, x, y, z, Cartesian coordinate system, and describe every point by a collection of three numbers. But in mathematics, we study geometrical shapes of all dimensions. We could say, okay, 4. We can experience four-dimensional universe because of time. What about 5 dimensions, and so on? What about infinite dimensional spaces? In mathematics, we study them. We are not deterred by the fact that we don't see them with our eyes, with our 5 senses. By the way, do you know what 5 senses are? Do you remember? There will be a quiz at the end, okay, so. So my point is, don't be fooled by this example, because here the difference seems to be subtle. Another objection I hear. oh, it's because we have language. In our language, these things appear. But guess what? Mathematics is a language as well. As Galileo famously said, it's a language of nature. In fact, mathematics is, I would say, it's like a source code language. It's like a binary. Every other language, as you know, every other programming language, every other program written in any other programming language, you break it down to assembler and then to binary, 0 and 1. So to talk about mathematics coming from some language is backwards. First of all, which language? English, Russian? Mathematical objects are expressed by different words in those languages, but mathematical objects themselves are imagined by all of us in the same way. So that's not a good way to argue it away, you see. In fact, as my star witness, okay, I'm calling Charles Darwin, who famously said that mathematicians, well, you read the whole quote. To save time, I'll read the punchline. Mathematicians seem to have an extra sense. So what this suggests is that in addition to the 5 senses that through which we experience the physical world, there is also this 6th sense, which I want to call the mathematical sense of the mind, using which we reach somehow those mathematical objects, like the ones I described, and like the ones which are much more sophisticated, like esoteric numerical systems, like periodic numbers, higher dimensional geometric shapes, large infinite sets, like what's so-called inaccessible cardinals, and so on. Mathematics is such a vast reservoir of knowledge, which, by the way, is a beautiful thing about it. It is even though it has sort of been hidden away, in a sense. In other words, we don't study most of this at school. We don't even teach our kids about how vast this archipelago of knowledge is. But in principle, it is all available. It is not hidden. And in fact, there are decisions by various supreme courts all over the world saying that you cannot patent a mathematical formula, like Pythagoras relation, Pythagoras equation, a squared plus b squared equals c squared. If it is true, if it is not true, you can patent it, it's fine. But if it's true, it belongs to all of us. It belongs to all of us. So even though the way things are set up today, it appears as if there is a small elite which has access to this knowledge, we have to realize that it is ours and reclaim it. You see, there is a certain democracy in mathematics, which, by the way, I want to say, it is reflected, for instance, in the fact that mathematicians, we have very kind of democratic relations between sort of like older members of the community and younger members of the community. That if an older, more mature, so we say, member of the community says something which is false, they will be criticized. There will be somebody who raises hands like, I don't think it's true. And I personally believe that's such an important thing that we have. It's kind of like a very important quality. And I'm not saying that other subjects don't have it, but it's just more difficult than the other subjects because we do have this sort of absolute sense of how things are, you see, because we all access them through this mathematical sense of the mind. So let's revisit the relation between math and physics, given what I have said so far. Physics describes the external physical world, the outer cosmos, if you will. And mathematics describes our inner mental world, our inner cosmos. You see? And because of that, I would like to argue that mathematics gives us an objective, scientific approach to the study of the human mind, to the study of human psychology. In fact, mathematics, in some sense, is a branch of human psychology. That's my point. Because we are not studying outer world. Now, in our Western world, in our Western culture, it sounds kind of surprising. And I am surprised myself, I have to be honest. I've been taught that the way to navigate things in my life is to look outside and figure out how planets move, how atoms collide, right? And so on. How DNA divides and so on. Well, it's kind of coming closer to home, but still, it's kind of still looking at the body as from the third-person perspective, right? That's our approach. Which, by the way, in other parts of the world, not at all. Carl Jung, who will make an appearance very, very soon, talked about the East and West as being introvert and extrovert. By the way, do you know this joke? Which mathematician is an extrovert? Which mathematician is an introvert? Don't give it away. Okay, you want to hear it? Okay. Thank you for indulging me. So the introvert mathematician is the one who looks at his own shoes when he talks to his or her colleague. And the extrovert, can you guess it, looks at the other person's shoes. We are introverts, okay? So physicists are extroverts. I guess that explains a lot, huh? Mathematicians are introverts. Of course, there are overlaps. It's not binary. We all have these qualities. It's just that, as Jung says it, which functions are superior functions, which are inferior functions. By the way, even the term extrovert, introvert were invented by Jung when he talked in his famous book, Psychological Types. Briggs-Meyer test, you guys familiar with this? So anyway, all of it originated from Carl Jung's work. So anyway, my point is, if we stop conflating math and physics, if we understand what mathematics is about, it's a study of ourselves, our inner world, suddenly the point of view changes. It's not that I have to constantly look outside and figure out how other things, move or interact. There is actually a lot to be learned by turning the gaze inside and learning more about myself. Who am I? You may have a certain opinion about it, but do I know the answer? And by the way, of course, this answer has always been on the minds of philosophers and inquisitive people, inquisitive minds. The famous saying on the Delphi, Apollo temple in Delphi, know thyself. It's an interesting question because it's very hard to take it seriously because I've been taught by who I am. I'm Edward Frenkel, I'm a professor at Berkeley. I am, a star of, as Louis kindly introduced me, right? So there are all these attributes. And it's so easy to believe that that's what I am. Well, that's the persona, that's the mask I wear, obviously. And I hope I'm doing a good job. By the way, do you know where the word persona comes from? Do you guys know? Persona, by sound. In the old days, the masks were not only used to cover the face, but to amplify the voice. So persona is a mask. That's the origin of the word. And we can learn, oftentimes we can learn a lot just from the etymology of the words we use. That's not the whole story. It's part of the story, yes. But it's not the whole story. And so, here, what I want to say is that mathematics, what I love about it, is not some voodoo stuff. Because of course, all the sages throughout, since time immemorial, have been telling us, have been telling me, Edward, look inside, find out more about yourself. But I could always dismiss it. I could always say, I don't know, that's not for me, or it's not scientific. It's mystical, And so I could easily dismiss it. I could discard it. I could say, I'm a scientist, I'm a mathematician. I don't need this pseudoscientific stuff. But now, guess what? I realize that mathematics is actually exactly going in the same direction. That's what I've been doing all my life. And I fell in love with it. And I found beauty in it. And that beauty that I discover in mathematics, it's not some abstract beauty which is separate, which stands apart from other beauties. The beauty of art, the beauty of music, the beauty of friendship, of love. It's the same. And in fact, there is neuroscience research, which shows that the same regions of the brain are activated when the mathematician experiences the beauty of an equation, like e to the pi I equals -1, or it's a famous one, but we have so many. The same regions of the brain are activated when mathematicians experience, and everybody's a mathematician, let's be honest about it, according to what I said. We just don't know it yet, maybe, but everybody is a mathematician. Picasso famously said every child is an artist. The problem is we don't preserve that sense as we grow up. Same goes for math. Every child is a mathematician. That's what I believe. So when we experience beauty as mathematicians, it's the same beauty. It's not different. It's like this mathematical beauty. This is artistic beauty, or beauty of a poem, or a beauty of a relationship. No, it's the same beauty. You see, so that means that mathematics actually points us to our own true nature, to who we are. But because mathematics is something scientific, it's something objective, it's the most objective of all sciences, I heard someone say. And I agree. Then we cannot dismiss it by saying that it's something that somebody came up with, that's something that's not true, that is not founded, that is not on firm foundation. It is on firm foundation. And what I will argue in the remaining time is that actually our discovery and our sort of absorbing of new mathematical ideas is just like integrating what Carl Jung calls psychological archetypes into our lives. And in a very real sense, when we do that, when we bring these ideas into our collective awareness, new dimensions of reality can open up to us. So let's talk a little bit about this. So Carl Jung founded what's called the School of Analytic Psychology in the 20th century. And the main tenet of analytic psychology is this idea of collective unconscious, which he describes as a common psychic substrate of suprapersonal nature, that is to say, nature transcending any specific individual, that is present in every one of us. And its building blocks are the archetypes. How many of you have heard about archetypes? Okay, cool. Teeny bit, okay, good. Well, same. I mean, I've read some Jung, but, well, maybe all of you, but okay, so I'm not going to boast, so, but do I still understand, I understand it? That's the question. So you've heard about it, right? So I think that, in fact, a good entry point into Jung's ideas is a portal, if you will, into Jungian ideas, is thinking about mathematics and the origins of mathematics along the lines that we have been discussing, you see. So, in other words, we don't have to study it right away or learn right away what Jung had done, but we can actually enter his theory through this sort of back door, which I hope will become actually the main door. In fact, this idea goes back to Jung himself. You see, he was really worried that even though he had accumulated this enormous body of evidence by doing his main work, which is, apart from being a philosopher and psychologist and so on, he was actually a psychiatrist. He met with real people. And there are records of him, like on this day he had 9 patients, and these days he had 10 patients. He himself estimated that he had analyzed 80,000 dreams. And some of his ideas, he was an empirical scientist. He did not come from philosophy. He did not try to develop his theory kind of like from general principles. He was led to his ideas by working with real people, with his patients, by trying to help them heal themselves. And in this process, he discovered these regularities, these patterns in our psyche, you see, which he called, so that led him to the idea that there is a substrate which is common to all humans, which transcends personal, it's called collective unconscious. And these various patterns or like building blocks, or you could say structural elements of this collective unconscious called archetypes. But he was worried that his ideas could be easily dismissed, that people could say, that's so subjective. There is no scientific proof of it. And many did. He was troubled by this. And he was searching for what he wanted to call Archimedean point. You know, like this Archimedes maxim saying that you can move the earth if you have this kind of a sturdy point, and you use a lever. He said, we are in a difficult place because the study of the psyche, which is what psychology is, doesn't have an Archimedean point because we study psyche with a psyche. And he said, well, physics is in a better place because we study physics through the psyche, because everything we can learn, we learn from in the physical world through our perceptions, but perceptions are filtered through our mind. But in later years, he came up with a fascinating idea that actually mathematics could help in this regard. Now, he was not a mathematician. He actually had trouble at school, according to his biography, Memories, Dreams, Reflections. He was kind of like Charles Darwin saying, I wish I knew more mathematics. But he had this idea that natural numbers, which are, of course, at the cornerstone of all of mathematics, come from an archetype, in our collective unconscious, which he called an archetype of order. And he saw how numbers appear in dreams. For example, appearing in dreams have different connotations, have different meaning. So, for instance, he talks about mandala, which is the symbol of wholeness, which he says it appears in a dream, for instance, or in other experiences at a point when certain conflicts are resolved or transcended. And it usually always has a circular form. So here is a mathematical archetype, a circle. And there is a cross. So number 4, quaternio. The number 4 kind of symbolizes this sense of unity and wholeness. Okay? So that's what he focused on. And he wanted others to pick this up. One of his students, Marie-Louise von Franz, his favorite student, in my opinion, kind of took up the torch. He told her to work on this, and she wrote this beautiful book, Numbers and Time, I think in 1978, late 70s. Marie-Louise von Franz. And so she made the first steps. And then there are a bunch of other books that she wrote, and there are notes of her lectures on the subject, which have really inspired me, as well as Jung's work, of course. But at some point, she was basically saying, okay, well, I want to find somebody who can actually take this up, because that's all I can do myself. And so thinking about this, and what we discussed earlier, I came up with this. This hypothesis appeared that actually all mathematical objects and ideas come from archetypes in our collective unconscious, which I call mathematical archetypes. And the beauty of these archetypes is that they are observer independent. So they are part of the psyche, of the common part of the psyche. So all minds, think about this model. All of our individual minds are connected to this collective unconscious. Collective unconscious, maybe I'm gesturing like this, but maybe more like this, like cloud. Imagine like cloud. We connect to the cloud, right? So when we work on our computers and so on. And that cloud, that collective unconscious, is a repository of all of those mathematical archetypes, as well as other archetypes, like shadow, anima, animus, the self, and so on. Far be it from me to say that everything is just mathematical archetypes. Unfortunately, a lot of my colleagues kind of get to this point, and then they try to subjugate everything to mathematics. I don't believe that. I believe love and math are the two pillars of humanity, in some sense, and so neither of them subsumes the other. What we need is balance between them. It's like yin and yang, it's like extrovert, introvert, it's like left brain, right brain, and so on, you see. So there are other archetypes, but mathematical archetypes have an advantage. They are objective. We perceive straight lines, or perceive through the mathematical sense of the mind. Imagine, conjure up straight lines, or points, or spheres, and so on, in exactly the same way. Whereas other archetypes, which are more like determining our interaction with other people, our sort of our aspirations, our loathing, our frustration, and so on, like shadow, like animus, and so on. They are realized in each of our lives differently. So they are subjective, even though there are certain underlying patterns. But in the case of mathematics, there are patterns, and also the realizations are the same. That's the idea. And therefore, it is the easiest place to start, in my opinion, in our exploration of this collective unconscious. Now, what is unconscious? My time is limited, okay? So I just want to give you an example. Do you guys know about this? How many of you know about the arrow? Okay, well, maybe half. Okay, so but not everybody. Okay, so I invite those of you who did not raise your hand and who was truthful also. Do you see an arrow in this picture? In this, of course, everybody has seen it. I'll help you. You see? When I first saw this, and interestingly enough, this was around the time when I got interested in Jungian psychology, about 11 years ago. I was so shocked by this. It's like, how could I not see that? And then it dawned on me, I had always seen it. It just was not above the threshold of my awareness, conscious awareness. I have always seen it. And that's the whole point of modern advertising. Subliminal advertising, it's called. Google it. It's the whole idea, to embed these symbols, which will affect you sort of under the radar, but will affect me. So the point about unconscious, the difficult aspect of this concept, is that how do you know it's real? Because by very definition, right now, I'm unconscious of it. So you have to demonstrate that there was a point when I was unconscious, and yet it affected me. So then it came back to my conscious awareness. And this is used in advertising all the time. You know, famous examples where they flash something like drink Coca-Cola on the screen. So that it's not perceptible to the eyes, and yet you can then measure that a much larger number of people after seeing it will go and buy Coca-Cola. Which, by the way, if it is so easy to affect us with one picture like this, can you imagine how many hidden things are embedded into a political ad? And here we are. Here we are. So the best way to continue on the road we have been going is to deny that there is such a thing. It's collective unconscious. That's what I believe. This example, this arrow, captures something essential, which I believe is not really part of our education today. The realization that our mind is limited, that there are blind spots. And moreover, as you go deeper, you also realize that the mind is actually actively working on preserving those blind spots for various reasons. What we call repressed contents and so on, childhood traumas and things like that. All right, so that's just an illustration. I'll give you one more. Do you see what's going on here? From A to Z. You can buy everything from A to Z on Amazon. Okay. So now, you see, let's go back to this idea of mathematical archetypes. This was, by the way, a screenshot of a video that I did recently. I recently launched a YouTube series, which I call The Aftermath. Some of you may know that I wrote a book called Love and Math, which was published in, well, actually, Louis mentioned it in his introduction. It was published in 2013 and is now available in 19 languages. And a few years ago, I decided that I want to write a sequel. And I came up with a good name for it, Aftermath. Everybody seems to like the name. But then I thought, why should I do it as a book where we have other ways available today? So I decided to try to do it as a YouTube series with like a video book. A lot of people today actually listen to books, like audiobooks. But here it's kind of a video book where each video is like a chapter in the book. And I feel like it gives me more opportunity to interact with the listeners, with the viewers, with the audience, because I don't I thought I had things planned, but in fact, as I go along, I actually learn more. That's the beauty of this type of interactive process. So anyway, what I'm talking about is, I have so far 2 episodes, so, and you can find them, I'll put a link at the end. You can find them online. And of course, my time is limited, but if you like to learn more, you can watch those videos that I give a lot more detail on all of these ideas. But here is kind of a sketch of what I mean by accessing mathematical archetypes. So my point is, archetype by definition corresponds to a kind of structures, inner structures or dispositions of the mind, of the human psyche, which in recurrent typical situations sort of lead us to very similar emotions, thoughts, dreams, and so on. And likewise, mathematical archetypes kind of throw images into our mind. So when I think about a line, I'm saying, what I'm doing is that I'm accessing the archetype of a straight line, the really, really straight line, which has 0 thickness and so on. One which, as I argued earlier, does not really exist in the physical world around us. But it does exist in collective unconscious, in my opinion. And when you access, we access the same archetype, and it throws exactly the same image into our minds. You see, so that's the idea. That's the basic idea. Now, I want to say that there is a lot of indirect evidence for what I am proposing. Because some of the greatest mathematicians and theoretical physicists are on record saying what a great role unconscious has played in their discoveries. You see? So, Einstein Albert Einstein, I have no doubt that our thinking goes on, for the most part, without use of words, and beyond that, a considerable degree unconsciously. He also said, imagination is more important than knowledge. He also said, I'm enough of an artist to draw freely on my imagination, suggesting very clearly that imagination is not something that is captured by thought alone. How different from what we hear today about our new so-called AI systems, which will soon supposedly replace us as humans, with artificial intelligence. What they do is they follow computer programs. They follow algorithms. And anyone who has studied theoretical computer science knows that not everything is computable, not every problem that can be stated mathematically can actually be solved by a particular computer program, or by a particular algorithm. The halting problem cannot be solved. That's the realization of Alan Turing, the father of modern computing, who, in his very first paper, in which he theorized the framework that we use to this day for computation, the framework of Turing machines, he proved a theorem. Essentially, the first theorem he proved was the impossibility of this framework to be always to be applicable in all cases. The key word is uncomputable, undecidable, incomplete. Gödel's incompleteness theorem is, of course, very closely related. Tarski's theorem, the impossibility of expressing truth by syntax alone. Rice's theorem about the difference between saying the Turing machine in principle cannot decide semantic properties, and so on. That's probably, it would be subject for a whole course, I guess. So I'm just indicating some notions. You see, it's very important to listen to what these giants of thought told us about the limitations of thought and the limitations of computation, the limitations of algorithm. Now, we may come up with a new paradigm for computation with quantum computers and so on, in which a lot more will be possible. But within today's paradigm of computation, there are some really hard bounds that have been proved mathematically, hard bounds on what we can do, what we can achieve, you see. And this is where I think it's important for us to actually talk about the origins of mathematics. Because you know how interesting that one area where ChatGPT and similar programs have not been successful is in discovering new mathematics. Huh, how interesting, because they are products of mathematics. Very, very elementary mathematics, one could say. Because mathematics of the 19th century, basically linear algebra, vector spaces with inner product. And of course, some ingenious ideas on top of it. But the core, this is the kind of mathematics I can explain to students in my linear algebra class in Berkeley within a week, within a few hours. You see, so what about, in brackets, what about the rest of mathematics? Who ordered that? If already these programs will take over and will kind of subjugate humans, right? So, but the point is to realize that the fact that these mathematical problems, which are born out of mathematics, are not so capable of discovering new mathematics, take it as a hint that mathematics actually has something that is beyond mechanical computation, you see. And our great ones, Einstein, Eugene Wigner, I kind of cut off the quote. He's saying that our mathematical thinking happens so deep in the subconscious, unconscious are synonyms, that the thinker is usually not even aware of what's going on inside. André Weil, a great French mathematician, every mathematician worthy of the name, is French, okay, so, has experienced, if only rarely, the state of lucid exaltation in which one thought succeeds another as if miraculously, and in which the unconscious seems to play a role. Right? So it's not like one person said that. Henri Poincaré, another great French mathematician, it is by logic that we prove, but by intuition that we discover. And elsewhere, he explains that intuition he considers it to be quite apart from thought, from logic. You see, of course, they go hand in hand. I'm not trying to separate them. Of course, the best results are achieved when we integrate them. But we go on a fool's errand when we try to pretend that these human qualities, these human abilities, human capacities that we have to acknowledge, appreciate, and celebrate, our creativity, our intuition, our imagination. We are going on a fool's errand when we pretend that it's all contained can be captured by logic and reason. Another great French scientist, philosopher, Blaise Pascal, said, "The heart has its reasons of which the reason knows nothing." Right? And that is that the last step of reason is to understand there are infinitely many things beyond reason. So reason can bring us to that spot. You see, so that's the beauty of it. Reason and logic actually can bring us to the spot where we appreciate its limitations. And that's the beauty of mathematics. It's a subject which is aware of itself. It's aware of its own limitations. Within mathematics, you can prove that you cannot do everything. Gödel's incompleteness theorem, Turing's work on undecidability, the halting problem, and so on. You see, so in fact, Marie-Louise von Franz gave Poincaré credit as being a co-inventor of the collective unconscious. She credited Jung, of course, Sigmund Freud, who was Jung's teacher and mentor for a while. Then they kind of parted ways, but Freud had this concept. And Poincaré, the mathematician Henri Poincaré, is credited by Marie-Louise von Franz as a co-inventor of the idea, or co-discoverer, if you will, of the idea of collective unconscious. So maybe before I go to this, I have a couple of minutes, so I just want to say, I want to give you an example of a mathematical archetype very quickly. And the example is the archetype of a flat space. And so what I want to argue is that mathematical archetypes exhibit exactly the same qualities and exactly the same aspects and properties as the more familiar psychological archetypes. And so in the video that I mentioned, that episode 2 of the Aftermath, I talk about 3 aspects of archetypes. One is if we are unconscious of it, which we're not aware, we can be, as it were, under the spell of an archetype, influenced by an archetype. For instance, if I think that I am like a level-headed guy, I never raise my voice, and so on, Even though in reality it's not the case, but I will kind of pretend that that's how archetype of shadow realizes itself, influences us. The first aspect. Second aspect is projection. If I'm denying I have this quality, I will project it onto others. I will surround myself with people who are shouting and always in conflict and so on. And I will blame them. It's like, oh, what are you doing? I am a quiet guy. Why are they all yelling? Right? So, and the third one is acceptance, realization, and integration, which gives me a choice to be level-headed or to be a little bit, to express maybe my strong opinions and so on, but I have a choice. So I claim that the same thing can be seen, can be experienced, or can be observed with mathematical archetypes. And here's an example. The idea of a flat space, the archetype of a flat space. We were under the spell of this archetype when humans believed that Earth is flat. Because it's the first, unconsciously, because they didn't even think that there were other options, you see. Same as for me, thinking that I am not, that I'm level-headed and not prone to, to lose my temper. You see, what happened about 2,500 years ago was that Pythagoreans and others around the same time in other cultures understood what it was all about. They brought the archetype of a plane. Plane is a two-dimensional flat space, like this blackboard extended to infinity. They brought it into our collective awareness. Well, first in their individual awareness, but then of course it propagates. And they understood that what it is, the plane is a geometric shape. And there are other geometric shapes. There's a sphere. There is a hyperbolic plane. And they asked, which shape is it? Is it our surface of the Earth? Is it a plane or is it a sphere, for example? And then they asked for evidence. And evidence, there was plenty of evidence to see that it's not flat. For instance, during the lunar eclipse, you can look at the shadow, no pun intended, of the Earth onto the moon. And there was one recently, by the way. They happen rarely, but not so rarely. You can see that it's not flat. It's round. But nobody bothered to look. Or maybe they looked, but they did not connect the dots. Like, look, you believe that Earth is flat, but you're not looking at the shadow of the Earth. Or when a ship approaches, you first see the mast, and then the hull. And if you have a higher elevation, you will see it sooner, showing the curvature, right? So that's how mathematical archetypes work. And now, of course, we can look back and remember how many years, if you look at the history. Actually, today there are people who deny that Earth is spherical. But for a long time, it was kind of something that people were not so sure about. You see, it seems like now we are out of the woods. But I don't think so. Because in fact, I think we're still under the spell of an archetype, but now of three-dimensional flat space. At least I am. I perceive the space in which we are right now, the space of this auditorium, as a flat Euclidean space, meaning that I can draw three coordinate axes. Or, a fast way to explain it is that this whole space of our universe can be filled with bricks of the same size, like boxes. That's very different from other geometric shapes of dimension 3. Now, for example, there is such a thing as a three-dimensional sphere. How many of you know what a three-dimensional sphere is? Three-dimensional sphere. So now, terminologically, there is a ball. The ball is the interior of a two-dimensional sphere. The sphere itself, like the surface of the Earth, is two-dimensional for the simple reason that there are only two coordinates that you need to pinpoint a location, latitude and longitude. So the sphere is two-dimensional, and locally it looks like a piece of a plane, which is why it was reasonable to believe for people who could only observe their small neighborhood, couldn't travel far, to believe that it's flat, you see. But now imagine going one dimensional higher. Three-dimensional sphere as being the boundary of a four-dimensional ball, so to speak. You see, this is not at all something that we study at school. It's not at all that people have thought about it. So we are kind of in the same place where we were at the time of Pythagoras, believing unconsciously, being under the spell of the archetype of the three-dimensional flat space. But what if our universe, our space, is not flat? Now, we know for sure that the four-dimensional space-time is not flat. But who can imagine four-dimensional space-time as a geometric shape? And so on. I cannot imagine three-dimensional, bent three-dimensional space. Imagine like the three-dimensional flat space, but bent in the same way as a flat plane can be slightly bent to form a beginning of a sphere. So there are some very practical, in my opinion, consequences of viewing mathematics as coming from archetypes and seeing the way we perceive the world while being influenced of those archetypes unbeknownst to us. And so then the question is, what are other blind spots in my awareness, like flat Earth or like flat three-dimensional space? And this is where I want to end with this quote. From Carl Jung. It's important to, I believe it's very important to at least investigate this idea of this hypothesis of collective unconscious. Because if we take it seriously, it follows that our view of the world can be only a provisional one. If the subject of knowledge, the psyche, is in fact a veiled form of existence, not immediately accessible to consciousness, then all our knowledge must be incomplete, just like mathematics. And moreover, to a degree that we cannot determine. I think it would be a breath of fresh air if more of us today will take this seriously. Thank you very much.
Thank you very much for a very nice lecture. Any questions or comments?
Sorry.
Oh, yeah.
Yes, so you said in the beginning that mathematical laws are objective, and then you tried to kind of elaborate on what do you mean by it, right? So I would say the more down-to-earth point of view would be that math is certain constructions which we have in our imagination influenced or inspired by our perception of physical reality, right? So
that is a typical approach.
yeah, so we could say, if we imagine some civilization far, far away in the universe, which is subjected to the same physical laws, but they're biologically different from us, they might have very different mass, right? They might have concept of integers, maybe circle, we don't know. They might not have the concept of quantum field theory, right? It's not clear, right? So in that sense, you only prove that mass is as objective as basically human psychology, right? Which means like
in this for us humans.
So yeah, it's like on our planet it's universal,
right.
but outside
I'm
of
not
it,
making
maybe
any,
not,
any
right?
statements about consciousness in general. The consciousness may have other realizations in other civilizations. It's a valid point. I'm focusing on, I wake up in, this morning I woke up in Stony Brook, New York. The day before in Berkeley, California, I wake up and I look at the news, I think about stuff, I go to shopping and so on. So I'm actually operating in this particular universe. So I'm very curious about what could happen in another universe, but I'm observing certain patterns in my psyche, in my mind, in my awareness, in the world around me, which lead me to a different understanding of what mathematics is. Now, I'm not yet ready to speculate what other mathematics there could be, and so on. I think it's already interesting to try to investigate. And please, as you know, as one of my favorite sages, Jiddu Krishnamurti, always says, don't take what speaker says on faith. Investigate yourself. Let's investigate together. So, to your point about we imagine them based on the experience of the outside world. I have tried to quickly explain why I believe this doesn't work. Because first of all, how come we all imagine the same, right? So that means our psyche is structured, our minds are structured in a very similar way.
Not always, actually. You made this point also that you never had problems with students of Berkeley not understanding what like an abstract straight line or circle is.
That's right.
But I think I heard there was experiments with like deer farmers, some of them far north, they'll be asked a simple question like, look at this photo of the moon, look at this photo of a golden coin. What's common between them?
Right.
And they fail to answer. Like
Right,
we know that
sure.
common is a circle.
So that's also
it's not true that
That's right.
we all have this universal
That argument is
unconscious.
familiar to me as well.
Right.
And my answer is that there are blind people also, so not able to see, right? So the question is whether it is a situation which is unchangeable, that these farmers, if they spent time with me or with other mathematicians in which we discussed what the sphere is, whether they would be able to exercise that muscle and also have the perception and an image of a straight line, of a sphere, and so on. And my contention is that most people will, if they put their mind to it. Likewise, I don't speak some languages. It doesn't mean that somehow I cannot learn them. To me, it's an innate capacity of a human mind, but it's not like a child does not have it yet. So we have to also go through a certain process to acquire those skills, so to speak. My point is that they come from something which is in principle built in, inborn, you see. Now, and the second point is, this would still be okay, kind of like, if all of mathematics was about Euclidean geometry and stuff like that, we can observe in the physical world. But we do not observe today higher dimensional symmetric shapes. We do not observe periodic numbers. At least I don't. We do not observe inaccessible cardinals. So where do they come from? And I believe, and then somebody could say, okay, but very few people know about this. To which my answer is, well, if they wanted to learn, nobody can stop them in principle. These things is available, and I contend that anybody who learns this, who puts an effort, will actually will be able to conjure up those mathematical objects and study them and discuss with others without any problems. And they will appear to them in the same way. That's what I'm trying to say. All right.
Any other
But
question?
To be continued.
Yeah. Any other question or comment? Yes.
You called math and love the two pillars of reality. How do you see the difference between the two? You call them two pillars. What distinguishes love from math, and what is their difference?
Right. What distinguishes love from math? It's very similar to what we talked about in connection with mathematical discovery. So when people like Einstein, Wigner, André Weil, and Henri Poincaré, and the list goes on and on, say that in my process of discovery, there is a certain element which is not just pure thought, just pure logical reasoning. And then they call it intuition, imagination, and so on. And like I said, I mentioned Einstein's quote, intuition is more important than knowledge because, he continues, knowledge is always limited, but imagination is what makes the world go round. So then, the question is, they're suggesting that imagination is beyond thought, beyond logic and reason. So how to explain it? Now, if I could explain it by thought, in some sense, I would repudiate myself. The explanation cannot be found in thought. It is found in experience. So, yeah, I say, there is something that one can experience when one knows that it is beyond thought or beyond logic and reason. To which our usual response, and that would be my response maybe 10 years ago, show it to me. I don't believe it until you show it to me. And this is where that's why Jung was so concerned. That he said it can be dismissed easily by saying that it is not provable by this, but you see how it's a catch-22. I have created certain conditions for the arguments that I will accept. I say things which are real are only things which can be reproduced in the lab serially many, many times. But I have created these constraints. So why should I be surprised that some things don't fit into those constraints? Whose fault is it? However, now my new point is that there is a lab. Mathematics is a lab for that, which is beyond reason. And that's the irony and paradox. Math, which is a paragon, mathematics paragon of logic and reason, actually brings us to the point of realizing that there is something beyond. How do we realize? By studying the question of the origin of mathematics and observing how these mathematical objects appear in our minds. And that then becomes a lab which we can then take to the next level by accepting the possibility that there is indeed something that is not serialized. And to put it simply, when I fell in love, I fell in love once. I cannot reproduce it. You see? So.
And oh, got to go up.
If you say that the mathematical objects are inherent to the brain at birth, in what sense are they part of the collective unconscious? Or in another sense, are they categories of the understanding different from the other archetypes that are learned and not innate to the brain?
Well, so the terminology is that according to the Jungian terminology, archetypes are all inborn. What is acquired is a particular manifestation or particular images or feelings or emotions that a given individual experiences when this archetype manifests itself. For example, in dreams. For example, by the way, there's so many things to talk about, like myths. So like Joseph Campbell, the hero with 1,000 faces. The fact that there's certain basic structure in myths which are found across cultures. So that's another indirect confirmation. So in that sense, mathematical archetypes are no different. The difference is that for most archetypes, they're all inborn. But they realize themselves differently. So there is immediately subjective element in how when we touch upon an archetype, the way it manifests itself in my life, in your life, and so on will be different. But mathematical archetypes have the special quality that they manifest themselves identically as well. Which, by the way, if I look at any object and somebody else looks, our perceptions will always be different because there will be different angles. But there is only one angle when we think about a straight line. Think about it too, right? So now, about the brain. So Jung changed his opinion. I think it's important not to be locked in a particular understanding of how consciousness operates. For instance, it's quite possible that there are certain hidden structures in the brain. And you could even argue that those structures were informed by evolution. For sure, I think this creates a very nice model. We should also be open to the possibility that there are some other mechanisms by which these archetypes come into being. We should not lock ourselves into sort of like make an ontological commitment, so to speak, of where consciousness comes from. I think we can all, whatever our view on consciousness is, we can all study this phenomenon together. Maybe it comes from the brain, maybe it comes from somewhere else. There are definitely common structures. They may or may not be explained by the structure of the brain. And Jung, in some of the works, was suggesting that they may very well be explainable. But then in some other works, he argued against it. So I don't know.
Hello. So Jung talks about will to meaning as the primal
Will to?
meaning of life.
Meaning of life.
The will to meaning. Jung talks about this in his work. Man and His Symbols. I read that book.
Right. Okay.
So and also like Arthur Schopenhauer, like they all talk about will to power, will to.
It sounds a little bit more like Freudian terminology. By the way, Man and His Symbol is, Jung only wrote one chapter of it, there are like 5 chapters. So I'm just not familiar with this term. You may well be right. But anyway, let's continue. So
Yeah, so do you think the current AI systems lack this will that the human beings do? And is that do you think is that the reason why AI systems can't come up with new mathematics?
because they don't have will.
They don't have will to find new things.
Look, I mean, at the end of the day, I do believe that there is something at play for which we don't have terminology yet, or we don't have language yet. So for example, I think it's a reasonable approach, what you described. So you're saying will. A computer program doesn't have a will, and maybe to discover mathematics, you need will, which, yeah, I can attest to that. It's a hard work, okay? So, but for me, I find it more, how to say, resonating with me if I say it's because of intuition, because humans have this capacity, this innate capacity of intuition, imagination, which computer programs, in the sense, again, in the sense of computation, understood today, Turing machines, Church-Turing principle, and so on. Church-Turing thesis, and so on. Maybe in the future there will be other paradigms of computation in which intuition will also somehow naturally appear. But today, I believe, computer programs lack that. So I call it intuition, you call it will. And I think we can kind of like agree that maybe this, in this context, these are synonymous. You see? Does it make sense?
So you speak about the idea of the Jungian archetype as something which is inherent to the individual. And yet it seems that the nature of mathematics as not only a globalized formalism with rigid rules, but one which in turn builds upon a set of axioms to some degree of necessary incompleteness, are resting and nested upon each other, building up towards these higher, more complex geometric models that you speak of. After all, if we study any mathematics course, we understand that one can't reach graduate topology without understanding undergraduate algebra. And as such, is it necessarily that we are verifying the existence of archetypes when we understand an undergraduate classroom or through teaching a farmer about the existence of an infinite line we cannot necessarily perceive? Or is it that we are verifying the rigidity and necessary existence of the formalisms that we structure mathematics on as a fundamental science?
I mean, look, here's the point also I want to make. Again, don't the great Jiddu Krishnamurti, don't take what the speaker says on faith. Let's investigate together. And it's a very, very legitimate question. I would like to make a confession. You know, I'm a knowledge addict. You know, I'm an addict to certainty. It's only in the last couple of years that I am barely starting to feel comfortable not knowing or saying, I don't know right now. Because Edward 1.0, you know, my previous version, would immediately jump to argue with you and try to explain what are the gaps in your argument and so on. And now I'm kind of like, okay, well, that's great. First of all, the fact that you asked me a question, I'm very grateful. It means that you found it interesting, at least, what I'm saying. And what more can I ask, honestly? It's a beginning of a dialogue. That's how I see it. I'm not trying to present some dogma here. I'm trying to present a possibility, a hypothesis. That's why I call it hypothesis. And at the end of the day, one could always say it's not provable. The proof is in the pudding, or the proof is in the kiss, or the proof is in this interaction. That's the proof. You see? And so then, from that perspective, all I want to say, let's talk about it, you know, after the lecture. Let's continue the dialogue. Let's exchange notes. Let's take each other seriously, and let's take and let's learn from each other.
Okay, well, I think it's a good point to stop. Thank you very much, Edward.
Thank you.